Good morning, everyone. So today is the sixth session of the workshop on nonlinear structural mechanics using Python. And basically, till the last session, we completed the main aspects of frame analysis using Python. So we started with bar, beam, and then frame elements. So the next step is looking at, and all that was linear. So in all that we have seen so far, we had a linear relationship between the applied forces and uh, the displacements. So it's yeah. So until now, we had looked at structural elements. Basically bar, beam, and frame. And we saw different aspects of the code, assembly and others. And we saw that in every case, we had to solve a system where we had a global stiffness matrix K multiplied by a displacement degrees of freedom vector U is equal to some known force vector. So this was the system that we solved until now. So what this says is that if this is the input, we're specifying the forces and we're getting some output. And this is some reduced stiffness matrix, which has taken care of the boundary conditions and so on. So this is some kind of input to the system and this is output to system. And the input output relationship is linear. Therefore, if you multiply the force by 2 times, the displacements we get will be multiplied by 2. So the input output relationship is linear. So whatever you feed in, suppose you feed in F1, you will get U1. And if we feed in F2, we get U2. And this is our structure. Let us call this structure some S, right? And if we feed in, so we have a relationship S of F is equal to U. So if this is the condition, then as long as the system is linear, it obeys U1 plus U2 is equal to S of F1 plus F2. Or in general, you can also multiply by arbitrary scalars. Alpha F1 plus beta F2 will return alpha U1 plus beta U2, which is basically alpha S of F1 plus beta S of F2. So this is a very, very convenient and very strong assumption. And this makes problem solving very simple. So because of this, we have superposition of forces. We can superpose two solutions to get the third, and a lot of things are easy. However, in real structures, we have things such as P delta effect, bifurcation, uh, inelasticity, and then maybe failure. And we have um, nonlinear boundary conditions. And in general, we also have some kind of large displacements, large deformation. So if you see what these are basically, so the first one is P delta effect. That is, you have a member like this. It is simultaneously subjected to some axial force, and it can also have some kind of lateral loading. So that lateral loading can be transmitted as some kind of a moment M. So if the length is L, the force is P, and this moment is some alpha PL. So what happens? So this beam will be initially deflected in some shape like this, and this P is acting upon the deflected shape. So this could be the lateral deflection delta, and this P is acting upon delta. So at every section, there is an additional moment which is P times delta. So this is the additional moment at every section. Therefore, if you look at the tensile forces at the bottom of this beam, in addition to whatever is given by the moment, applied moment M, this moment can be the applied moment, M of x, say y bottom by I. This is the stress due to, this is the tensile stress at the bottom of the beam due to the applied moment. But it also has got a component plus P delta of x yb by yb. So this there are additional stresses caused due to the eccentricity of the applied force with respect to the deflected center line of the beam. So the beam has to be designed for these. Otherwise, we might design the failure stress to be this, but the stresses that are actually occurring, the stresses are higher than that. Therefore, the beam will fail at a load less than the design load. Therefore, we have to consider P delta F, right? Then other idea is that of bifurcation. So if you take a column, same thing, you take a column, and then you there's no moment. You just set alpha equal to 0 in the above problem. You apply a force P. Okay, so this, what will this result in? This will make the right end of the beam move inwards by some delta x, and this delta x, as long as the force is less than a certain limit, will be just PL by AE. However, beyond some point, this is not the only solution. You start getting multiple solutions. So one of the multiple solutions is the buckled solution. So if you look at a plot of this delta x versus P, so one solution is it's linear with the elastic slope. So this will be L by AE, sorry, AE by L. And the other solution is it remains linear. So and beyond some point, you can have a different solution. So there is a certain point at which both the solutions are stable. That is called the critical point. This is called the critical point. And beyond that, you have a drop in load. So initially, so this is also a possibility. So you take a beam and you sufficiently brace it sidewards, and then you apply a force. You can go along the initial straight line path without incurring any buckling. If you prevent buckling by some means, you can ensure that it is the beam remains straight all the time. But if it is free to buckle laterally, and there is a buckled solution, so you can find out what the buckled solution is. So maybe you can take it as a homework. So you cannot get it directly for this case, but in this case you can get. So think of a beam subjected to a force P and a moment M, which is some alpha PL, and this alpha is very small compared to 1. So the beam has got cross-sectional properties EI and assume axially rigid. Therefore, until it buckles, it cannot incur any lateral deflection. So under these conditions, solve for. So in case you want symmetry, apply another equal moment. M is equal to alpha PL this side also, so that the beam bends in a symmetric manner. So that the maximum lateral displacement is at the middle of the span. So you can solve for the lateral deflection at the midspan. As a function of P. And you can plot it, right? You can also plot this. And yeah, so this you can do. And you can also do one more thing. You can obtain a P delta x curve. That is, delta x is the displacement of this point towards inside, and you can plot P versus delta x also. So this requires some work. You can get the lateral deflection directly, but from there getting this delta x requires some work. In that, for that you have to use the fact that the beam is actually rigid. So anyway, I'll post this. You can do this. This just there's not anything with coding or structural finite elements. This is just a conventional strength of materials problem with a slightly nonlinear effect of P. So you can do that. So when you solve this problem, you will see that you get some solution like this. So one solution is the beam remains straight, in which case there'll be no delta x because it is rigid. And beyond some point, it undergoes buckling. And that point is known as the critical point, where you can transition from one solution to the other solution. And beyond that point, the buckled solution is stable. So that is the other case where nonlinearity is becoming important. So we will we will not get to the other solution unless we allow large deformation. So that's another case where nonlinearity has become important. Then we have inelasticity, for example, yielding. So you take a beam, subject it to a midpoint load, and keep increasing the load P. So at some point, the stresses at the bottom of the beam, say sigma B, will reach the yield stress. And beyond that point, the cross-sectional stress distribution will be something nonlinear. Right? So initially it is like this. Once this bottom reaches the yield stress, beyond that, the cross-sectional stress distribution will be kind of nonlinear. So the actual part of the section that is contributing to the stiffness is only so much. When it is yielded, the stiffness is kind of zero, if you assume it is perfectly plastic. So eventually this if you keep increasing the load, it becomes this, and you have a plastic hinge. So what happens is the beam will stay. So at the center, the entire section has plastified. So this section will be resisting a moment MP. And if you look at the force displacement response, say P delta curve, initially it will be linear. Then as this section is becoming plastic, as it slowly becomes plastic, you will have a loss of stiffness, gradual loss of stiffness, and finally everything will be lost. So this curve is also nonlinear, and this nonlinearity is arising from yielding, which is a material nonlinearity. Then we can have failure. So if it is ductile enough, you'll have plasticity. But if you have some brittle material, there'll be some members that are failing. And that will also result in a nonlinear P delta curve. So this I'm not going to explain much. It's obvious. Then you can have nonlinear boundary condition. That is, for example, you can take the simple case of a spring with a mass. And then say I have another wall here with another spring hanging out. Right? I have another spring hanging out here. So what are the boundary conditions for this problem? You can say that you can write down the equations of equilibrium. So as long as this, so let us say this distance from this point to this point is some delta m. Say it is some delta max. So you can apply whatever kind of forces here, and this is going to displace by some delta, right? So if this delta is less than delta m, the equations of equilibrium are that F is equal to K delta. But if this delta is greater than or equal to capital delta M, then what is the total external force is F? What is the internal force? Internal force is 1. So if you draw a free body diagram, before this mass contacts this part, it is only a force K delta here. But after this mass contacts it, you have a K delta by this spring. You have something here. Let us call it K delta 2, where delta 2 is the compression of this spring. And you have a force, net force F. Right here. So here it is some K delta plus K delta 2. What is delta 2? So delta 2 is basically, delta 2 is just delta minus capital delta M, if you see. Right? So here if you see, the equations of equilibrium are like this, and here the equations of equilibrium are like this. So if you write an expression for delta, so delta is equal to either F by K if delta is less than delta M, capital delta m. And in the other case, what it is maybe f plus k capital delta m divided by 2k, I guess. Yeah, if delta is greater than or equal to capital delta. But you see, this itself depends on what it is, right? So you don't have a direct solution. In this case, if you see the force displacement response will springs are resisting it, then the slope will just multiply by 2. So if this is delta, this is f, this will be the response. So again, it is nonlinear. It is a combination of two linear slopes, but that doesn't mean it is linear. So bilinear is also nonlinear. So this is a kind of nonlinearity called contact nonlinearity. And what I just demonstrated here is a linear, it's a 1D contact. And in 2-dimensional or 3-dimensional bodies, you can have things like you have a balloon. You can have a balloon, and you press it against say the wall, right? You can press it between two walls, and you actually don't know which part of the balloon will be in contact, right? So it can have a contact area A. So their balloon has some internal pressure P. And this we actually don't know this area, right? So the condition is over this area, the balloon is flat, and then the rest of the places you have some pressure P. So we neither know the force that is acting on this area nor the area itself A. Therefore, this is a contact problem. So the contact problems arise in various applications in mechanics. In the context of structural elements, rod-like elements, there are some special cases where it occurs. Then you can have all kinds of large deformation. That is where we started this workshop with. I said we have a cantilever beam with a tip load, and as it deflects, you will have the beam bending in this direction, bending in this way. And as it bends, the tip of the cantilever will be retracted towards the wall. And this cannot be calculated by linear theories. Right. So these are the cases that require nonlinearity, and all of these nonlinearities you can either put under geometric, material, or boundary. So geometric is when you have large deformations, large displacements, or rotations, strains, deformation, whatever. So in general, it is large deformation. And material is when you have so ideally a linear elastic solid is linear. Everything else is nonlinear. So if you have a nonlinear elastic solid, it is nonlinear, which means it has got some geometric effects. You can have a linear inelastic solid, linear inelastic structure, such as a plastic beam, elastic plastic beam. So that is material nonlinearity. So this is like you can have plasticity, you can have viscoelasticity, viscoelasticity, or you can even have nonlinear elasticity. Nonlinear elasticity. So these are having certain specific meanings, but I don't have the time to explain them. You can just look up. This all easily available. So plasticity is permanent deformation. Viscoelasticity is time-dependent recovery. And nonlinear elasticity is you can have completely recoverable strains, but the relationship between stress and strain is not a straight line. And boundary, as I said, you can have some kind of contact nonlinearity. So let's start the problem for today. So here is a simple nonlinear problem. We have a 3-bar, you have a 2-bar truss. You can think of it as 2 bars, and this is also something like a bar. So we are subjecting it to a force F, 2F, and it is symmetric. So we'll analyze half of the structure. So our goal is to get a relationship between this force F and the displacement of this top point P. So how many degrees of freedom does this structure have? How many free degrees of freedom are there? So how many totally how many degrees of freedom are there? So I said in the beginning of our workshop, degrees of freedom is the number of independent number of components or number of variables you have to specify to completely know the configuration of this system. So how many degrees of freedom are there here? These are truss members. So
6 degrees of freedom, sir.
Yeah, you have 3 nodes. So you have 6 degrees of freedom in general. But you say here, let us call it 1, 2, 3, 4, 5, 6. So you know that D1, D2, D5, D6 is 0 by boundary conditions. And by symmetry, what is 0 by symmetry? D3 is 0, right? So this is a line of symmetry.
Yes.
And displacements normal to the line of symmetry should be 0. So D3 should be 0. This, if it moves rightwards, then from the other end, it looks like it is moving towards. From this end, it looks like it's moving away, but it is symmetric, so it has to be 0. So only free degree of freedom is D4. Right? So this we'll model it as a 1 degree of freedom system. So how do we do that? We'll first draw a free body diagram. We'll first draw a free body diagram. And this cannot move perpendicular to it. So there is some reaction coming from this side. Let us call it R. And it has to be equal and opposite. So this has to be R. What else? It is free to move vertically. So specifying a force to F. If you model only half of the structure, you'll have just F. F on this half, F on this half. Similarly, the spring stiffness 2K can be split into. Okay, that will do anyway. So this is like. So you apply a force F here. And you have a spring force. Let us call it Fs on half of the structure. So on the full structure, it will be 2Fs. So what is the reaction here?
F also.
No, it's F minus Fs. You have F downwards, you have Fs acting upwards. So for the net vertical forces, F minus Fs downwards. So this has to be F minus Fs. Okay, so this is the system we have. Now, okay, let the force in this member, let's call this member AB. Let the force in this member be some tensile force FAB. Right, now look at that joint. And this angle is some phi. This angle is some phi. So at this joint, if you write the equilibrium of forces, you have FAB acting thiswards, this side. You have Fs, and you have F downwards, and there is an R. So if you set the sum of all vertical forces as 0, we get F is equal to Fs, which is a force in the spring minus, sorry, it's not equal to force in the spring minus FAB. Okay, so what is the so spring constant is 2K, and force is 2Fs on the full structure. So 2Fs is equal to 2K times what is the displacement of this point? So the spring is getting compressed, so the force will be upwards, right? As V is positive downwards, Fs will be resisting the applied V, so it will be 2K times V. So Fs is equal to Kv. So this is equal to Kv minus the force in the member AB. Now let's suppose the stress in the member is sigma. The force in the member is some FAB is equal to sigma times the area of the member A. So assume that strains are small. Displacements and rotations can be big.
So here FAB, the vertical component of FAB is FAB cos phi. No,
Yeah,
sir.
sorry. If this is FAB sin phi. Yes. Yes, I missed it. So it has to be FAB sin phi. This is phi. Yeah. So this KV minus FAB sin phi. Yeah. How did I miss that? Yeah. It has to be FAB sin phi. So this assume that the strains are all small and the displacements are displacements and rotations can be big in general. So what do you say? What does this mean? You can say that so when as FAB is getting compressed, the cross-sectional area will increase a little bit due to Poisson's effect, but you can ignore all that and say A is approximately the original A naught. So yeah, the sign phi is important. I don't know how I missed it. It should be there. So it is KV minus sigma A. You can put an A naught here, doesn't matter. Sigma A sin phi. And sigma you can have the linear relationship. We are not considering material nonlinearity in the entire workshop. So we'll only look at geometric nonlinearity. So you can take it as E times epsilon. And what is epsilon? Epsilon is change in length by original length. So this, remember, we have assumed FAB to be tensile. So you take the positive string L minus L naught by L naught. So it is KV minus E times A epsilon. So epsilon is what? It is L minus L naught by L naught. So multiply the minus inside, you get KV plus EA sin phi into 1 minus L by L naught. Right? This makes sense. So the force is a sum of, this is the reduction in area because L will be less than L naught as FAB is under getting compressed. L will be less than L naught. So this quantity is positive. So when FAB is getting compressed, you will have a positive net force, which makes sense. Okay, so this makes sense. Next, what do we do? Next, let us. So this is okay. Okay, so next, what we can do is suppose we have one equation that relates. So this, what are the unknowns in this equation? V can be taken as known because we are inputting it. F is unknown. This angle is unknown because as it comes down, this will keep rotating. L is unknown. L is unknown. But look at the geometry. Can we find L? Yes. So L, use Pythagoras theorem. L square is equal to, let us say initially it is, so this is given as B, that is not going to change. It is B square plus what? Plus something square. What is the vertical height here? So this is the deformed geometry. Sorry?
H, sir.
H is fine. H is before deformation. After deformation?
H minus delta.
Yeah, H minus B. That is H minus B. So this gives one equation. This gives one equation for L. So we can eliminate L. What is the other expression? It is sin phi. So what is sin phi from here? Opposite by hypotenuse. Yes.
H minus V by B.
L.
L.
Right? That's tan phi. If you put B here, it's tan phi. So that's it. So we have everything that is required. Now let's summarize the equations of this problem, right? So here you don't expect to get a linear relationship. So we have L that is related to V as, so L of V is square root of V square plus H minus V the whole square. Then what is it? Then we have a sin phi. So I can say sin phi is what? This is also a function of the displacement. It is H minus V by L.
Yeah.
And this L is an L of V. And what else we have? The force. Force as a function of V is actually a function of these two. So that is nothing but, what did we get?
AV plus EA sin
AE
KV
sin.
okay.
Okay.
AE
Yeah.
sin.
So KV plus
EA sin phi into 1 minus L by L naught.
Yeah, sin phi of V into 1 minus L of V by L naught. Yeah, so this is totally fine. Maybe we can substitute for the sin phi so that we can get rid of 1. So we get f of V is KV plus AE AE is fine. Sin phi is H minus B by L of V into 1 minus L of V by L naught. So you can simplify this further as KV plus AE H minus V into 1 by L of V minus 1 by L0. Is that okay? Like something is not correct. I'll just check. 1 by, yeah, we don't have a divided by L. That's the issue. No, that's fine. H by L is fine. Yeah, I think this is okay. It is L. What was the final expression? It is L naught by L minus 1. Yeah, this is totally fine. So this is the expression for force we are having in terms of the displacements. So we can these two equations, this one and this one, together govern the response of this. So if I input V, so I can either input V. So just remember these two equations. You can take a screenshot if you want. So it's like one is AE. Yeah, this is one expression which is nonlinear in V. So this first expression, this first term is kind of linear, kind of looks like linear, but the second term is having a product of V with something in the denominator that's nonlinear. And L of V itself is a nonlinear function of V. So this is a nonlinear relationship between F and V. So you can think of this in two ways. You can specify the displacement and the structure does something and it gives you the force. This is a nonlinear relationship. Or you can specify the force, the structure does something. Let's call it something else, S2. This is a different function. And it returns V of F. So this is called displacement control loading. Displacement control loading. And this is called force control loading. So while doing experiments, there's usually this two choices. If you are interested only in the peak force, the failure force or something like that, what ultimate stress and things like that, you can do a force control loading. Whenever we are interested in the full behavior, people do a displacement control. They have the displacement under control and see what is the force that is required to cause a certain displacement. On the other hand, in force control, they just increment the force in some steps and they'll measure how much displacement is caused in the structure. So usually these days, displacement control loading is preferred because we have good sensors, we can have a good feedback system. We always do displacement control loading. Force control loading is slowly going out of phase, but it is cheap. It is usually cheaper. It requires less sensors. Now, our goal is to characterize the response of this truss using somehow. We only have the equations, but we have to know how it looks. So let's get to Python at this stage, and we'll solve it. So I'm taking these values as h as 0.5 meters, b is 10 b is 10 meters, and EA I'm taking as 5 meganewton per meters, 5 meganewtons. That is like 5 into 10 power 6 newtons. So now you can tell me what I should do next. So this is not any FE, right? You don't have any problem specification. This is just we are just going to plot this under displacement control. So let's just find L, right? We need K. So I'll take K is equal to, first let me take a small value, K is equal to 10. And then what I can do is I'll just plot this. So what should I do now? My goal is to find a relationship between F and V. So yeah, now you have to tell me so that I get to know how much you're comfortable.
We can write the first equation, sir.
Okay, but first equation, okay. So first equation is L is equal to
is NP dot SQ or T.
okay, h square plus, sorry.
B square plus
Okay.
H minus V the whole square.
Okay, but is
We
B
have not
defined?
specified. No, sir,
Yeah.
not defined.
Yeah. So, okay. So what can V be? We can, what to do with V? V can be, I'm interested in an entire range of V, right? So V increases from in displacement control loading. I'm going to increase V from 0 and I'm going to take it to some point, right? So I say initially V is 0 and say I'm slowly increasing it. And so here we don't have any linear elastic approximation. We don't have any linearity approximation. So I can go to large displacements and large rotation. So I can take this V starting here. I can take it to I can keep push. It's like I'm putting my finger there, and I am controlling the rate at which it moves. So I am moving it and I am measuring the force that is felt in my hands, right? So I'm moving it downwards, and at some point it will become straight. This will become straight, and I can even move it further. I can even go to the other side. So finally, my deformed shape can be something like this. Right, I'm moving it and I'm just coming to the other side. If you feel it looks unphysical, that it is crossing the spring, you can put the spring upside down. You can put the spring upside down and do the same thing. Nothing will change. The spring force is still K up. Sorry, the spring force is still K delta upward. So you can put the spring upside down and then pull this point as much as you can. The spring will just keep extending. Yeah, in case you feel pushing this will cause the spring to go through itself, which is unphysical, you can do this. So spring will be under extension instead of compression, but the direction of force will still be upwards. So that's fine. Let us. So we should be something starting at 0. So you can use this NP lin space. So lin space will generate enough number of points at some specified interval. So I can say starting at 0, then stop at let's go to a distance of 2h, right? We can go to a distance of 2h, and the number of points I'm interested in between, just to get a smooth curve, I'll take, I think it is num is equal to how many points I can take, maybe some 25 points. Okay, so this, now it's fine. Now given this operations are defined, so h minus v star star to what it does. So it's not going to take the vector v and do some matrix vector multiplication. It will take every element of vector v, subtract it from h, and square it, and then that will be another vector. So every element of that vector will be added with b square. Similarly, when we do np dot square root, every element of this vector inside the brackets will be taken square root, and it will return another vector, which is the vector of lengths. Okay, then what to do? What's the next step? We can use the second equation.
Yes, sir.
Yeah. So F is equal to K star V plus
A star E into H.
Yeah, I have anyway defined EA together, so no problem. It is
EA star
star
H minus V star
1 by
L minus
okay.
1 by L naught.
L naught is not defined, so what do? We'll define it. So in L naught is just at the L naught is the length at the beginning. So this L looks very much like 1. So I'll use capital L. So L0 is the L at the beginning, right? When V is 0, before any deformation happens. So I'll just I can either call it as L of 0, or I'll just copy paste this with V equal to 0. I'll just remove the V from this. So it is just B square root of B square plus H square. So this is 1 by L minus 1 by L naught.
Capital L, sir.
Okay. So we'll run this part. And I can plot V comma F. Okay, so we got a plot. It's too big. So this is the response. So initially, so this is for a small k, it's for k10. You start in this fashion. Initially, it looks something like linear elastic. Then it reaches a maximum force. So at some point, if you look at it, yeah. So at some point where h is 0.25 around that time. So h is 0.25 is half the height. Half total height is 0.5. So around that time, it reaches the maximum force it can handle. Then the force starts dropping. So beyond that, you don't need to increase the force to keep the truss deformed. If you release the truss at that point, it will automatically fall through this curve. It will fall through this uh, to a straight configuration. So when it is straight, the force you need to apply is actually zero. But still, although you have a zero force there, the stiffness is kind of negative, which means the truss itself will. So what it means is you gradually start pulling the force, pulling this point down. At some point, you'll experience the maximum force, and beyond that, the force will keep decreasing. And at h is equal to 0, v is equal to 0.5, the force is 0. When the two members are perfectly horizontal, we don't need to apply any force. That makes physical sense. But if you release the truss at that point, it itself will go through this branch, right? It will start deforming by itself because it has got a negative stiffness, and it will reach another point here. So at this point, what happens? You will again attain a maximum force, but uh, this
In the
force is
upward
upward,
direction.
upward direction. So beyond some point, the force changes its sign. So the maximum force, instead of applying downwards, you will have to start applying upwards. So you need to keep pulling the truss upwards to avoid it from deforming. That's what it means. If you release it, it will just go. So then beyond that maximum force, then again we need to apply some increasing force to deform the truss further. So sorry, decreasing force, but it is slowly the force direction starts changing to downward. So again, so this is up to a value of 2h. You can also plot it to say 2.5h. So what happens beyond that? Beyond that, you just have to apply a downward force. So this phenomenon is called a snap through. So you need to apply increasing force up to a point. Beyond that, the truss is unstable. It will it will just lose its stiffness. Then if we release the force, it's going to take some other configuration. So we need to decrease the force to avoid it from accelerating. And at some point, you need to reverse the direction of force. So the truss will try to pull your hand downwards. It will not move it will not move down under your applied force. It will pull your hand downwards. Then again, beyond some point, we will have to apply a downward force, and that force will keep increasing. So this is the nonlinear behavior of this truss. This is a very simple. So we just have two equations, one degree of freedom, and we have solved the problem. Right? This is a nonlinear displacement control loading. So this is a classic example, which is like first example in any nonlinear course. Right? This is the first example people take in any nonlinear course, and this is fairly nonlinear, and this comes only due to geometry. There's no material nonlinearity. Okay, so this we have got um, just by considering this large rotations and large displacements, no and small strings. Okay, so this problem is solved. Now we have solved the problem of displacement control loading. What about force control loading? Now all kinds of problems will arise. So think about it this way. So think of it this way. We have f as a function. We have f, let us call this f tilde of v. So f we have as a nonlinear function of v. This is fine. This is quite fine. And this, what is that function? That is this function, right? So given v, I just have to find L and substitute L and v into this equation and find f. Now, if suppose I specify v, suppose I specify f, can we find v? Okay, so this is a question. Now, before even answering such a V exist. Sorry, yes, such a V exist. So sometimes you may not have a solution, or sometimes you may have multiple solutions. For example, if I say the force is 50 newtons, right? Look at this response. If I say force is 50 newtons, how many solutions we have?
One solution, sir.
Why?
Oh no, like multiple solutions. 3 solutions are there, sir.
Yeah, we have 3 solutions. So if you take 50 newtons, let me copy paste this. Yeah, if I say the force is 50 newtons, and it is somewhere here, and at 50 newtons, I am able to have a displacement of something around 0.7, 0.6 or 0.7. Then I'm having a displacement of 0.2 or something. And I also have a displacement of about 1.5. So the truss can, these 3 correspond to 3 different configurations of the truss. So here the truss is kind of slightly deformed. So if we say A, B, and C, at A, the truss will be something like this. At B, it is like, it is close to the 0 point. So at B will be something like this. And at C, it has actually inverted. The displacement is more than 0.5. So at C, it will be something like this. And in all these cases, the force that we need to apply is only 50 newtons. So we have multiple solutions. Okay, that is one issue. Then how to find it? So if the structure is linear, what do we do in this matrix analysis? We are ultimately finding we'll look at the element stiffness matrix, transform it, get the global stiffness matrix, and after getting the global stiffness matrix, we will get a system of equations. F is equal to Ku. So ultimately, what we have arrived at is given U how to find F. When we do the assembly of the global stiffness matrix, that is what we do. Given U or how to find F, that we are getting. But uh, but they are getting U given F is very simple because U is just K inverse F. But here what it is, here F is some highly nonlinear function of V. It is not manually possible to find V given F. There might be ways, but I'm not sure. So you can do some algebraic manipulation, say write H minus V square as L square minus B square and substitute everywhere. So that may lead to something, but I'm not really sure. So this you can write as square root of L square minus B square. Still you will have an L and F. So you have this task of inverting a highly nonlinear equation, which we can't do. So what do? We use numerical methods. So numerical methods to solve for the unknowns. So given an equation y is equal to f of x, and f can be a nonlinear function. F is a nonlinear function. What methods are you aware of to solve this?
Euler's explicit, implicit methods, Newton-Raphson method, Simpson's
Okay,
method.
Euler's explicit and implicit is for ordinary differential equations, or for this is an algebraic equation. This is algebraic. So
we know
explicit. Yes.
If we know one root of the given equation, we can proceed with solving Newton-Raphson.
Okay, so you're saying if we know one. Okay, but how do we even know it has got multiple roots? That's the issue, right?
Yes,
Yeah. So it's right. Oh, so you said one Euler's. I'm not sure. So you said Newton-Raphson. That is okay. Then any other? This is what we are going to use. So Simpsons and all is for numerical integration, right? So you may have bisection. would have heard of bisection. Then
No,
you'd have heard of secant method.
secant method.
And
Yes,
then you
secant
would have heard
method
of
we should
something
know
like,
two roots.
yeah, if you have a repeated root, then people use secant. And you would also have heard of some modified Newton method. And there are several others. There are many such. And Newton-Raphson is very good. It has the fastest convergence. So we'll see Newton-Raphson. So what is the idea? Suppose we want to solve. Suppose we want to solve some f of x equal to 0. Right, so f of x can be some nonlinear function. Say it doesn't have to be a polynomial, but it can be like this. So this is the root. Suppose x is the actual root, and I want to get to this point. So you start with something called an estimate, and say, suppose you're somewhere close to the root. So you can approximate the root as. So you cannot find where the function is crossing the x-axis, but you can find where its tangent is crossing x-axis. So suppose this is xn, and you approximate the root as the point where its tangent crosses the x-axis. So let us say this is some xn plus 1, where the tangent to that point crosses x-axis. So if I want to find this, how do I do it? What is the relationship between xn and xn plus 1?
Xn plus 1 equal to xn minus f of xn divided by f dash of xn.
Yeah. So this is the numerical scheme actually, but you are again, when you're doing this division, there is some issue. This f dash of xn has to be non-zero. So what we can do is, let me write it in another form. I'll say xn is equal to xn plus 1. Sorry. I'll write the equation of the tangent, right? You can say f of xn is equal to f dash of xn into so wait, this is f of xn is equal to f dash of xn into xn minus xn plus 1. Right, so we want f of xn plus 1 to be roughly 0. So this is one thing. Now if I yeah, so I think it's right. So this goes to right. Yeah, this is fine. So this is the idea. So in the next step, what do? You take this as an approximation of root, then compute what f of xn plus 1 is. So it will be somewhere here. Then draw a tangent from here. So this will be xn plus 2. Then take what is the function value there. It will be here. Draw a tangent from there. So as you see, even graphically, we are approaching the root like this. You have something like this, and you're approaching the root like this. So to approach this point, you're taking a sequence of tangents, which eventually converges to this. Okay. So this is the rule. Now what do we have in our case? In our case, we have an what is the equation that we are solving? We are solving some f external is equal to f internal. We are balancing the external force to internal force, and this internal force is some function of u. So this is what we are doing in our case. So look at this expression. So f of v is the applied force f external, and what is on the right hand side is f internal. Now we are actually solving f external is equal to f internal. This is what we want to solve. So if u is the actual solution, this f external minus f internal will be equal to 0. F internal of u will be 0. F external does not depend on you because that is what we are specifying, right? F external is something given as input to the system, and u is given we are getting u as the output. So the internal forces depend on u. F external is just is independent variable, so it does not depend on u. So u is this, if u is the actual solution, but if u is an approximation, right? Say suppose un is an approximation. What do I say? I can say R is equal to F external minus the internal force due to Un will be what? Will it be 0?
Approaching to 0, sir.
Yeah, it will be approaching to 0, but not 0. Our goal is to make it as small as possible. So this is also a function of the guess. So un is some kind of a guess or an approximation, and it will not be 0. And whatever remaining value it gives, that we can call it as residual. So in nonlinear problems, our goal is to take the residual r of u1 to 0. And if we are really lucky, it may directly hit 0. But in reality, it never hits 0. We'll go very close to 0, but we'll never reach 0. But the convergence will be very fast. So the convergence is of second order if you have so it's r of h square. Right. So in every iteration, we get 2. Yeah, you can see it converges very fast. The error drops with the power of n square. Like with every iteration, the error drops by 2 orders. So our goal in nonlinear problems is to get the force residual to 0, to approach 0. So what is the equation we want to solve? We want to solve r of u1 equal to 0. No, r of u equal to 0, not r of un equal to 0. We want to solve r of u equal to 0, where r is the residual. Now let us set up a Newton-Raphson scheme, right? So what is the first step? What is the first step in Newton-Raphson?
We have to write the equation r of u equal to 0. Then we have to find out a root. Then we can.
No. Before I'm saying, while solving the problem, what do we need? So look at the graph. So we have a nonlinear function, and we are starting with some. We have to start with some point, right? So you have to make a guess. Start with a guess u0, right? Start with a guess u0. Draw a tangent there. See where it hits the x-axis and call it as the next estimate, right? So you start with a guess u0, okay? Then with u0, you can find r of u0, right? You can find an r of u0, call it r0. That's the initial residual. And when you start something, that residual value will be usually big. So don't worry about it, even if it is big. Okay, what is the next step? Now we know, so we are at this point.
We should predict the direction in which we should go. No.
Yeah, that's correct. Direction is nothing but the tangent, right? You are drawing a tangent there and you're seeing where the tangent hits. So you're initially at this point, then you want to draw a tangent with the slope of this function, right? So the second step is
either u0 plus some value or u0 minus some value, and find out whether it is tending to r0 is tending towards lesser value, then we can go in that way.
Yes. So this plus some value or minus some value, you can in general write it as r of un. I'll make it n now because this is the general scheme, plus some delta u. You force it to 0. This is the idea, right? You force it to 0. So the idea is r of u is 0. If you use the actual solution, it is 0. This is un, right? This is say this is un, and this is u. This difference is some delta u. So un plus u is some delta u. It's okay. So you said it is either plus some value or minus some value, but together you can write it as delta u. But delta u can be either positive or negative. Doesn't have to be positive always. So you say r of un plus delta u is equal to 0. What we can do? The Taylor series. So we get r of un plus, what do we get? Delta u times r dash of un plus divided by 1 factorial plus delta u square
f r double dash of un divided by factorial
plus higher order terms. You want to set this equal to 0. But this is also nonlinear in delta u. So the approximation we do is let these be negligible. Right, neglect these. Therefore, you get instead of so this will not be a perfect zero, but to let us find what is delta u such that it takes it closer to zero. So this is the dominant term. If we are fairly close to the solution u, then this will be the dominant term, because if we are very close to the solution u, this delta u will be small in comparison to u. Therefore, these terms will be negligible in comparison to the first two terms. So the initial guess has to be close. If the initial guess is wrong, we'll diverge. We'll not be comfortable. So the initial guess has to be reasonable. If it is fairly close to you, you can approximate this as roughly 0. Now solve for delta u. What is delta u? It is minus r of un by r dash of un. Okay. So but this delta u is not going to take us anywhere. So you just use a corrected estimate for the root. So you say un plus 1 is equal to un plus delta u. And this is un minus r of un divided by r dash of un. But what is r of un? R of un is
0.
No. R of un is not 0. R of u is
F
0.
external minus F internal.
Yeah, f external minus f internal, which is a function of un here.
Un.
Yeah. What is r dash of un?
Minus F dash.
Yeah, minus f internal dash of un. So this is fine. So finally, what do we get? You say un plus 1 is equal to un. So that's a minus here. And in the denominator, you get another minus. So it is plus the residual at un divided by f internal dash of un. So we can take this, we say delta u is equal to f external minus f internal of un divided by f dash of un. So this is the update you have to give to the displacement u. So after finding this, you update un plus 1 is equal to un plus delta u. Then how do we stop? So this iteration we can keep on doing. Well, when to stop? When to stop?
If that value is up most tending to 0, then we can stop.
Which value is tending to 0?
R of un plus 1.
Yeah, perfect. When r of un plus 1 is very small, we can stop. So let me take r of un plus 1, a small value of r of un plus 1 as so let me take the relative error in r of un as, you remember r naught is the initial residual. If I'll say if it is less than some 10 power minus 4, I'm going to stop the iterations. So very good. So this will work, right? So let's summarize the algorithm. So first have a guess. Sorry, have a guess u naught and find r of u naught. Store it as r naught. In the next step,
R of un plus del u equal to
no. Next step is actually iterative, right? So let us say keep doing, or I'll say do the following. Okay, so this is like do this while, what is the stopping condition? R of un or un plus 1 doesn't matter, is, so if it is less than some 10 power minus 4, we'll stop it. So you have to do it when it is greater than or equal to 10 power minus 4 times r0. So what should we do inside? So first step is inside this. First step is find r of un. Second step is find what else we need for the Newton-Raphson key. Yes. I can look at the formula. What is required here? R of un is the numerator.
R dash of un.
R dash of un. Yes. Then delta u is equal to minus R of un by R dash of un. Then what should I do? So this is giving me some
plus del u.
No. So first I have to update u. So un plus 1 is what? U plus delta u. Right?
Yes, sir.
Then in the next iteration, set un is equal to un plus 1 in the next. So the current iteration un plus 1 will be the input guess for the next iteration. So at every stage you should also check R of un. If it is small, then break the loop and come out. If it is big, then continue. Right? Big means it is greater than this. Small means smaller than that. So this is fine, but there is some issue. This works totally fine. But if you see, we made an assumption here. We said this is negligible when delta u is very close to 0. When delta u is very small, this is negligible. When delta u is small compared to u, it is negligible, which means our guess un should be close to u. So if we have big differences, if un minus u is very big, we may not get to the correct solution. For example, okay, it's taking time to load. Yeah. For example, in this problem, if I say f external is 50 newtons, if I start from here, it is unlikely that I will get this root. My Newton, if I draw a tangent here, I will mostly get to this root, right? I'll get to this root. Similarly, so I will not get this root. Similarly, if I draw a tangent somewhere here, I will not get to this root, but I'll get to this root. So if I draw a tangent here, yeah, I'll get to this root, right? So it's like I'll draw a tangent here, then goes here. So this way I'd get to this root. So depending on where I start, I will get to, it's because there are multiple roots, I'll get to any one of them. But I want to get all of them, right? So what I should do is, I should not do a single step. Should not increase the load in big steps. So this is important. I should not increase the load in very big steps. If I increase in very big steps, I may get, it may not converge first of all. And even if it converges, it may not get converged to the correct thing. So increase the load in small steps. So this is important. Whenever you do things in force control or even in displacement control, you have to increase the force in some small steps. So what I can do is, instead of applying F equal to 50 Newton all at once, I'll apply it as 5. First, I'll apply 5 Newtons, get the U. Then I'll increase another 5. So I'll get 10 Newtons, get the U. Then I'll apply 15 Newtons, then they get the U. So I'm increasing the load in some small steps. So for every increment, I have to do this. For every increment, I have to do this. So that's the only difference. So this entire procedure will be inside another loop, which is loop over load increments. That's all. Right? We'll loop over load increments, and in every increment we'll do this. Instead of doing it once, we'll do it in every increment. So this is fine. Only thing we need to calculate here is R dash of un. So let me calculate that. Right? If we calculate that, we are set. So what is our F internal? Is kV plus
AE into H minus V into 1 by LV is 1 by LV, L of V.
Okay.
L of V is square root of V square plus H minus V the whole square.
H minus V the whole square. Now R dash of V is minus F internal dash of V. So this is minus K minus EA into H minus V. Let me not skip any steps. I'll say it's minus K plus d by dV of EA into H minus V 1 by L of V minus 1 by L0. So it is minus K. So here I'll apply the product rule. So I'll get a minus. So I'll first differentiate the first term. So d by dV of H minus V is minus 1. So it is plus EA. H minus V will go away. You'll get 1 by L of V minus 1 by L naught. Minus the second. Here, no, that's what, there's a minus, but that minus gets multiplied with this and you get a plus, right? So H minus V, if you differentiate with V, you'll get a minus. So you get a minus EA. Then what? Minus EA. Now H minus V will stay back. So in this term, only the first term will contribute. Second term is a constant. So you get minus
1 by 2 into
L square. Is it right? 1 by 2 into L. Why 1 by 2?
Say L of V is square root of H minus V square.
Oh, okay. That will do. So it is first minus 1 by L of V the whole square into dL by dV. Yeah, we will do it step by step. Don't.
Okay, sir.
So what is it? L dash of V is here you will get 1 by 2 square root of H minus V the whole square plus B square. And whatever is inside you have to differentiate. So you get a plus 2 into H minus V. Then what is inside H minus V? You get a minus 1. Yeah. So this 2 gets cancelled. L dash of V is minus H minus V divided by. So this you can write as minus of H minus V divided by what is in the denominator?
LV.
L of V. This is just L of V. So write it. So it is minus K plus EA into 1 by. Now I'll drop the L of V. It's understood. 1 by L minus 1 by L naught. So you have minus here, a minus here. So you get minus EA H minus V. You get an L here and there's already an L square. So it's L cube. So this is R dash of V. And what is F internal of V? It is just negative of it. So it is K minus EA into 1 by L minus 1 by L naught plus EA H minus V by L cube. Okay, so this is fine.
H minus V
squared, yeah.
H and minus is also there. Minus. Okay, so minus is correct.
There's a minus here, there's a minus here, and there is another minus here. So that gets that's a minus, net minus, and this F internal is negative of this, so this is fine. Okay, so this we got F internal dash, we have F internal, we have F external. Okay, so we are set to solve the problem. Now let me go here. So before that, one more thing. So this is at k is equal to 10. If you want, we can find for other case. So I'll loop over. I'll take values for k in. So 0 I can take, which means there is no spring. It is just two truss members. I can take 100. I can take 500, and I can take maybe 1000. Right. So these are the different values of k I'm considering. So I can put everything after that inside the loop. And I'll plot also in a loop. But to understand which is what, I'll apply plot labels. So I'll say label is equal to k is equal to. So this is like formatting string. I think you know that because some of you have used it in your homework, that assignment. So use this colon to put whatever you want inside and format K. So here this will give you, and if you want, you can add meganewton, whatever, Newton per mm square, Newton meter square. So Newton per meter. So you can do that, and then finally you just say plt dot legend so that it will display the legend, and then say plt dot show so that it will show the plot. So it will plot all of them, and then we'll get the final answer. If you run it, yeah, this is the, so k equal to 0 is the blue line. So k equal to 100 also you have this sine wave. You have something like a sine wave, and as k increases, this the stiffness increases. So at some point for k is equal to 1000 and all, you don't have any drop in the load. So its stiffness is decreasing, but it increases again. It doesn't drop to negative. The force doesn't. There's no force drop. Force only keeps increasing. So so that is fine. We got this right. So this is the behavior for different cases. Now let us go to this case. Now let me choose the case k is equal to 1000 because of certain reasons. I'll tell you the reason, because if you say k is equal to 100, right? Say if you take the orange curve, and once you hit the limit point, once you hit the maximum force, you cannot increase the force beyond that. So that will cause some numerical issues in convergence. So you have to, but here that issue is not there. So it's like in a uniaxial testing, once you reach the ultimate load, beyond that the force cannot be increased, even if we are controlling the force. It will cause the specimen to explosively fracture. Instead, if we control the displacement, we can get it. Or you have to, or if you have a material which doesn't have an ultimate load, then you can increase the force under your control. There's no problem. The material will respond very well. So here, let me, for the moment, I'll avoid this orange curve and I'll look at the red color curve. So yeah, so we'll look at we'll solve this in a force control setting. So now what should I do? So I have K, I have L naught as h square plus b square. Then what else I need? B, A, E, H, they are already defined. So now I have to write a loop. So what is under my control? Under my control is what? Here I had displacement in force. Perfect. Yes, yes. So now I'll say force I'm increasing from. Suppose I want to get the red curve by force control. So I have to increase force in small steps. So force goes from 0 to some 1700. So maybe I'll increase it in some, say, so again, np dot lin space. Again, I can zoom in. So I'll start with a force of 0. Then I'll increase it up to say 1600. And I'll increase in how many steps? I can increase it in, say, 40 steps. I'll increase the force in 40 steps. Okay. Uh, then suppose I want the displacements. I'll say I'll initialize the displacements to zeros. Right? I'll just put zeros everywhere. Zeros of how many? 40. Or I'll just zeros of length of force. So instead of F and V, I can call it force and disp. And this is length of force. Okay. Now what should I do? I have to apply the force. I have to increase the force in steps. So I'll run a for loop over the force. So for I in range of. So do I have a starting point? Do I know the equilibrium point anywhere? So when force is 0, what is the displacement? Sorry. Yeah, when the force is 0, what is the displacement? Is it
0, sir?
Yeah, it is 0. So displacement of 0 is 0. But anyway, we're initializing it with 0, so no problem. So I don't need to solve for the first step. So I'll start with the second step and go on up to the length of force. Okay, this is okay. So I'm starting with 1 and I'm going. So now what is the current force? I'll say F external. F external is equal to force of II, right? I'm applying some force. Okay, then I want an initial guess. What to do for initial guess? I can call the initial guess V0. V0 is what? It is the, so I hope you understand what we are doing, right? So if we have, so my objective is I want to, so my objective is I have a curve like this. I have a curve like this. Starting here, and I want to, and I'm starting at 0, and I want to get to some force. So I'm increasing force in these steps. So at this force value, I want to find the displacement. I know the force. I want to see what is the displacement. So I want to start with an initial guess. So I'm currently at this step. So how to get to this point? I use Newton-Raphson. So I need an initial guess. I'll use this as my initial guess so that I see this. So I'll hit this force. Then here I'll find out the residual. Then hit that. Then again I'll find out the residual, and I'll slowly converge to this point. Similarly, from when I want to go from this point to this point, I have to start somewhere. So I'm using, say I'm starting with the previous displacement. Say this is Vi, and this is the next step V. This is the converged V. So this is Vi. I'm using this as an estimate. So what I should do, and this is the force. So I'll draw a tangent like this, then find out what is the force there. So at that force, I'll draw another tangent, find out the force there, and so on. Then it will converge. So I need an initial guess, right? Every time I want an initial guess. So let me choose initial guess as the displacement of previous step. So now I hope you understand why we have to do it in steps. Suppose I'm doing it in one step and I want to get the force here. And we have some curve like this. If I have no idea of how the curve is, every time my initial guess will be every time my initial guess will be at the origin, except 0, 0, where the force and displacement are 0. I have no other idea of any intermediate point. So if I don't increase the load in steps, I have to start here every time. So I have to start here and sorry, I have to start here, then here I'll draw a tangent that goes somewhere here, and then this goes somewhere here. Sorry, it may go somewhere far away actually. So here you see there's a change of curvature. Here the curve is concave downwards, and here it is concave upwards. So when we have such points of inflection, you have this Newton-Raphson could diverge. So that is the reason, and we assume that U is close to UN. We assume this, therefore, always increase the force in small steps. And therefore, you start with a guess estimate, which is, since you are increasing in small steps, you can estimate, you can start with an estimate that is just the previous iterations, not previous iteration, previous displacement value. So if I want to find out the next displacement value, I'll start with V here, because I know this point is actually lying on the curve. So whenever you want to use Newton-Raphson, you need points on the curve. You need to start with a guess that is on the curve. If you start somewhere else, it's not going to converge. Okay. So we'll do that. So V0, what should V0 be? So if I want to get current force, what should V0 be?
It is the displacement of
previous one, II minus 1. Perfect. Then what is the next step? So I have an initial guess. Now I can do the Newton-Raphson iterations. So I'll call this step as Newton-Raphson iterations. So what is the code here? I'll tell you it. I'll tell that. So it is while some condition. What is that condition? You can see here. What is the condition? Here we wrote down the algorithm, right? What is the condition? While, where is it here? Yeah, while R is greater than some tolerance. So I will do that. So now so first I need to find R. So R is what? R is that expression. So I'll write a function for that so that it is this thing, right? R is basically this. Yeah. So let me write I don't need to write a function. We're only going to use it here, right? So I'll say R is A star V plus EA star H minus V star 1 by 1 by L. Sorry.
1 by L.
But this is not R, this is F. So R is negative of this. So I'll just call it F internal. Because the scheme will differ depending on we are using R or F. Right? So this is F internal. What is the derivative? Also, let me call the derivative of F internal as some J for Jacobian. Right? I'll tell you why it is J. And what did we compute it as? This thing, right? K minus EA into this thing plus this. So I'll write that it is K minus EA star 1 by
L minus 1 by L naught plus
EA H minus V
double star 2
divided by
L double star.
Okay, but you should be careful. I have not defined the deformed L, right? So I have to define the deformed L. What is L? L is square root of.
We have already defined also.
No, that is not. That is for the. That's the thing. So first thing for the force controlled solution, I have not defined L, and this is actually much before.
Yes. Displacement control.
Yeah. No, but that's not the issue. Even if I write L is equal to something here, even if I write L is equal to something here, that will not change with every iteration. That's the issue. So here I need an L that change. So I have already got the solution up to a certain value of force. So for that value of force, there's a displacement, and for that displacement, there's an L. That update will not happen unless you define L inside the loop. Okay. So this has to be inside the loop. So it is NP dot square root of V square plus
H minus V the whole square.
Okay, but I don't have a V. In this, I only have a V0.
This.
Right? So wherever you have V, you have a V0. Right? V0 is the initial guess. And this is the F internal. This is also, I can call this as some F0. Okay, so this is the F0. This also I can put as J0, which is J. Okay, so now what is the condition? While R or while F int. So F int can be negative or positive. Let us use the absolute value. Well, absolute value of F int is less than or greater than 10 power minus 4 into F0, right? I hope you're understanding. So the condition I put here is I want this R to be great. This relative error in the residual, R of un by R naught should be greater than some tolerance. So that tolerance I'm stating it as 10 power minus 4. I can even define that. So I can say tolerance is equal to, so I don't have to make tolerance equal to say 10 power minus 4. And put minus 5, no problem. So this is when it is greater than some tolerance. So it is tall, and this should also be absolute value, because sometimes the force is negative, as you saw. So negative means the sign has to reverse. So we'll deal only with the absolute values. Okay, while this condition is true, what should we do? We should find F int. F int is this. So this is the internal force. And Jacobian. Right, then we have G. Okay, then what should we do? Update V, right?
Yes.
So initially I have an L. This also I can write it as V is equal to. So these are the initial values of this before we start the iteration. So can put this as V is equal to V naught is equal to this thing. Or to be consistent, I'll write V naught is equal to V is equal to this thing. So F naught is, so now I don't need the V naught. I can just put V everywhere. H minus V, L minus V. Okay. And this L should also come below. Okay, yeah. So now it is consistent. So the idea is we start with the initial value. This L naught is undeformed. Then we enter the loop. We're taking load in small steps. So external force is not going to change. That is the input. Then we are setting something as the initial guess for V0. That is the displacement of the previous step. Then we are setting an estimate of the length. Right? For the estimated initial displacement, this is the estimated length. And for the estimated initial displacement, this is the estimated initial residual force or initial internal force. And you have an estimated Jacobian. I also need R0. So R0 is, what is R0? What is R0? R0 is the residual. So it is Fx minus F int, right? And that is also R initially. Right. So this is just R. I don't need F int here. It's R. Is this okay? So this is initializing before the iterations. You're making a load increment here. So this loop is over the forces. You're first applying, you're taking the external force. You're taking a guess. So these are guess values. So this is initial guess. So initial guesses are V naught, L, F naught, and J naught. Then you're calculating the force residual. You calculate the force residual. Then you do the Newton-Raphson iterations. So when the force residual is greater than some tolerance, the relative error in force residual is greater than some tolerance. So it's like by abs R0 is greater than some tolerance. It's the same thing, but in this way, you'll be able to see it's a relative error easily. You start with the initial force. Internal force is F internal kV, this thing. So J is this. Okay, so this is then what is the update? V is equal to, so delta V is what?
Minus R of R divided by J of.
Yeah, it is R divided by J. Yeah, if it is so R is nothing but F external minus F internal. So F external is not going to change, but F internal changes in every loop. So F external minus F internal divided by J. So note this J is actually derivative of F internal, not R. So if derivative of R is appearing, you need a minus sign. It's the derivative of F internal, so there's no minus sign. Okay. So then update V. So V is equal to V plus
delta V.
Delta V. Okay. Now let me put some lines. Suppose sometimes the Newton-Raphson may not converge. So I'll just give a exit condition. So in case, so suppose it doesn't converge, if I have a while loop, it will just keep running on for thousands and millions of iterations. So I'll say in case Newton-Raphson does not converge. So in that case, I can set a cutoff number of iterations as if. So I'll count the number of iterations basically. So I'll say iteration count. I'll call it count is equal to 0. And as soon as I start an iteration, I'll say count is equal to count plus 1. Okay, so every time I do an iteration, the count will increase. But suppose I have gone through, say, some 100 iterations. If count is greater than 100, then I'll break the loop. It's not going to converge. But while breaking, I'll print Newton-Raphson takes too many iterations. And in this case, it is greater than 100. So it will print this in case there is an issue with iterations. Okay, if it is, so this is the case if it does not converge. If it converges, what should I do? If it converges, automatically the loop will be broken and it will come out. It will come out of the while. So I'll go out of if. I'll go out of the while, and if it has come out, it is converged, then I will update the current displacement is what?
V plus V, sir.
Is V, yes, it is V. Perfect. Now, in case it did not converge, I'll also give an exit here, because if it doesn't converge in the 10th load step, in 11th, of course, it will not converge. So I'll give another if count greater than 100, I'll break it. And I'll say aborted. So print aborted. So this will update the displacements. And I think, yeah, that's it. So I'll zoom out a little so that you can see the full code. So start with.
In the last code bracket.
Okay. Oh, brackets. Okay. Okay, thanks. So yeah, so overall, you're starting with something. You're starting with an initial guess. Find the force residual. If it is not under control, increase the number of iterations. Get into the iterations, and keep doing these iterations and keep updating V until it is very close to the solution. Once it is close, break the loop and come out. And if it had not exceeded the maximum number of iterations, then set the current displacement to B. So this is this is the case. And then I'll just do one thing. I'll store the previous things as in displacement control. I'll just store the values as VD and FD as V comma F. So in the previous case, V and F are vectors. So I'll just store them so that I can put it on the same graph. And here I'll get displacement and force. So let me run everything. Okay, Newton-Raphson did not converge. And let us see what is II, at which stage it not converge. Okay, right at the first stage it did not converge, which means there is something wrong. So we'll see what it is, right? So we'll start with this initial guess. V naught is B. P is fine. L is fine. L. R. So let us print all these things and check what is F external. F external is 41. That's okay. And then F internal is F internal is 41. So why it did not converge? Oh, I'm not updating R. So I have to say R is, so R will always stay in the initial value, right? That's the issue. So after finding F internal, I have to update R. So R is F external minus F internal. And this I'll just put it as R by J. So now it has to converge. It's a simple problem. It has to converge. Notebook has been changed outside of this session. Yeah. So I'll run it. Okay, now what is the issue? So F internal is some junk, F external is something else. So F so this is at a different II, I guess. This is what is II here. II is 13, and what is K? K is 1000, right? Okay, maybe let's try increasing the number of iterations. Okay, F internal is diverging due to some reason. It is not correct, probably. We have to. Okay, this is V0, that's the issue. It has to be V. Inside the loop, it has to be V. This is the problem with copy pasting. This has to be V everywhere. And L is also not getting updated. So the geometry is changing, therefore L will change. The internal force will change, and the Jacobian will change. So we shouldn't have V0 anywhere. L0 is fine, 1 by L, yeah. Now it has to converge. Okay, now there's no error. So F external and F internal, they are very close. F external is 1600. That's what we wanted the simulation to run to. And F internal is 1600.001. So it's okay. It has converged. Now we can plot it. So I'll say PLT dot plot. I'll plot displacement comma force in red color, and I'll call the label as force control. And I can also plot displacement and force in, not displacement force. What is it? VD and FD, which is D refers displacement control. This I'll plot in green and I'll label it as displacement controlled. Yeah. Say displacement control. It's enough. And I'll say PLT dot show. Right. So let's plot this. Yeah. So only one line is shown because they are over each other. If case you want to see this, I'll say minus dot. Yeah, see, so this is the dotted ones are the force control points, and the green line is the displacement control, which we got earlier. And so I hope you realize what the whole point is. Getting the displacement in terms of force for such a nonlinear problem is impossible. Therefore, we are using a numerical method. And in particular, since it has got only 1 degree of freedom, we are using the Newton-Raphson method. So by using the Newton-Raphson method, we are increasing the force in equal increments. So you see the x distance of, so somewhere here the x distance is very close. Where the curve is flatter, the x distance is bigger because we are taking fixed increments in force. So these dots are where the forces are, and the where we are taking the force steps, and green line is the displacement control thing. Now, you see what happens if I slowly, if I increase this, if I decrease this k, suppose I make k as 500, you see what happens. Then one more thing, I can also, sorry. Yeah. So I'll also suppress the second one, or I'll have the second one. I'll have both, but in first one I'll make it as dotted line, and I'll make it thicker. I'll make line width. I'll make line width 2, and the second curve I'll make a thinner line so that even if it is second, it will be visible. This I'll make line width 0.5. Okay, so now let us run again. Okay, one more thing. This now this has to stop at 500, right? So I'll turn on. So yeah, so you can see that what is happening here.
There is a difference in force.
There's a difference, right? There's a difference, and there's a difference between the force control and the displacement control solution. And we'll also see why the difference is coming. Now, let me make this value even smaller. Let me make it just 200. I'll make it 200, and here also I'll run for k 200. So this is 0, 100, and 200. What happens here?
Difference is getting large.
Yeah. So yeah. So why do you think this happens? So when we increase the force, what is happening here? We are increasing the force initially. We're reaching the limit point. Beyond that, what is happening? Beyond that,
it is going large. It is undergoing large strains.
Yeah, it's going it's jumping from this point to this point basically. So the problem here is when we do load control, we cannot see the actual curve. So for example, this is the equilibrium path. So this is the equilibrium path of this curve, this structure. So beyond this point, the force has to decrease if we want to keep the displacements under control. But we don't have a control on the force. We are only increasing the force in some small steps. So what happens at this point? The solution it is looking for, it has to go in this direction, but we are forcing to increase the force. We are not allowing the force to decrease. If you have to have controlled displacement, we need to decrease the force. That's what the curve means. But we are not decreasing the force. So from here, it is trying to draw a tangent, and the tangent is meeting only here. So initially, I think the fourth step is 41. So it's like initially it is 0, then 41, 82, 120, 41, 82, 124, and then we are going to 166. After that, as you exceed that point, it is exceeding the maximum force in this locality. So that force can be achieved only here. So it jumps. So this is snap through. So this is what I said. Now go get back to the problem. If you see this, you apply when you hold this point and you're pulling it down, you will experience changes in force. The force will initially increase, then decrease, then become negative. Then the truss will be pulling your hand, and again beyond some point it will become downward force. But if you just apply a constant force, if you start pushing with your finger on top without holding it, and you slowly increase the force, once you reach this point, and you further increase the force in your finger, the displacement will just jump. The structure will snap to the other configuration, and from there you have to increase the force further. So at this point, it cannot sustain any further increase in the force. Therefore, the structure this undergoes a snap through instability. So yeah, that's the idea. So this is a demonstration of snap through instability. This is under a large deformation, and you're able to capture it very well. Okay, so this is one example, and this is already saved in your classroom. Yeah, this session 6 is already saved. You can find this code there. So we have some more to do. This is just a truss. Our next target is to do a frame, right? But before that, there are some concepts to be covered. But I think module 3 is mainly done. So I did an introduction to nonlinear analysis, and we also did an iterative solution of one problem. So next I think we have time. No, we don't have much time. So I'll tell you what we'll do in the next class, and then we'll close today's session. Then the last session will be on Wednesday, on Gandhi Jayanti. And in that session, we'll finish nonlinear truss and frame analysis. That should, yeah, I'm not sure how much we can finish, but at least that stability part we have to skip. And yeah, we can do nonlinear truss and frames. Yeah, so we have had only 4 hours on nonlinear, and remaining 10 hours we did on linear, but that's okay. If you do linear, if you're confident with linear, nonlinear should be easy. So in the rest of this, what we'll be doing is we'll derive something called, so what we did just now is, it's not good. So the equation we were solving for is we had an equilibrium equation. We had a nonlinear geometry. And we had linear stress strain. So these 3 together is resulting in a system called like this: F internal is equal to F external, and F internal is a highly nonlinear function of the displacements. And now we just had one.
Yes. In the snap through region, the structure is accelerating, sir.
Yes, we are not modeling it correctly. If we do a dynamic analysis, it will accelerate. But in this case, what is happening is it's not able to find a static solution nearby. So so if you remember when I started it, I said, how many do we have a solution? If you give a force, initially we had 3 solutions. But since we are increasing the force gradually from 0, it always captured the closest solution. When we go to the limit point, there are some issues. We cannot capture this. If you increase the force little bit, the only solution it has is here. So from here, it is directly going to this. But in reality, what will happen if we apply a force more than what it can sustain? It has got mass, so it will accelerate. So instead of the, so it's not a big thing. So it's like, in reality, if you apply a force which is yeah, so in reality, if you apply a force F which is greater than what can be sustained by the structure, so what it can sustain is the maximum of this. So just suppose the spring is not there. Right? Suppose the spring is not there, you have an FAB and you have FBC. So it is, if suppose it's greater than FAB sine theta plus FBC sine theta, what happens? F will be greater than, let's just make it F2 FAB sine theta because of symmetry. Suppose this is the case, then these things have got mass, right? These bars have got some mass. So the remaining will be F minus 2 FAB sine theta will appear as mass times acceleration. Mass times, say, some U double dot. Right? So when you apply a force that is greater than what is required, the structure will accelerate. It will undergo an acceleration, but it will not accelerate indefinitely. It will accelerate and it will go to this configuration. Once it goes to that configuration, from there again you can keep increasing the force. So that is what will happen. So it is true, in reality the structure will accelerate, but what we got just here is not, it is not a dynamic solution. It is just that the static solver is not able to find any nearby point, so it is finding the next point, which is here. But in reality, the path it takes from this limit point to this point will be an accelerated solution. Yeah. Is that okay?
Yes, sir.
Yes. Okay, so what I was saying is you have these three conditions. These are the take it to the next page. So what we did today is this for a 1D system, for 1 degree of freedom system. Now, what will happen? Suppose we have an entire truss. Say we have an entire truss like this. And I'm applying, suppose I apply some force here. So these members are under compression and they can buckle, right? They can actually buckle like this. And that is also a large deformation problem we have to do it. But this is like many degrees of freedom. Now, how am I going to mix these two? That is the main idea of next class. So this is done. For a 1D of system, we got this system of equations, and this is solved by Newton-Raphson iterations. Now, for a multi-degree of freedom system, first we have to get this F internal equal to F external. How do we get that? So how do we get that? So we get that by something called this. So until now, whatever we did was getting this. So in the case of linear structures, F internal was Ku. And F external was whatever it is. So for nonlinear structures also, we have to get this Ku. And whatever we did to get this Ku, all the assembly, so we did with started with statement, problem statement, then assembly. And inside assembly, we had an element stiffness matrix. And that we transform. And then we plug it into the appropriate global Kg and Fg. Then from there, we enforce boundary condition. And then we solve. Now this full setup has to get inside the Newton-Raphson. So what will happen is we'll have the old code, we'll have the old truss code. So let us call it truss. Right. So this old truss code, what it will do all the 4 steps. Now this entire thing is only going to give you F internal. And F external, we are supplying it, no problem. F external, we are supplying it. So once you get F internal, this entire thing has to get into Newton-Raphson iteration. So this will be under some while r less than r greater than 10 power minus 4. So the entire this thing will get into a while loop. This will be this entire solution, right? This will be done for every iteration of Newton-Raphson. Okay, good. This will give us F internal, but a Newton-Raphson also requires something else, right? Apart from F internal, what do we need for the Newton-Raphson to work?
F dash.
F dash, okay, but F dash is in the case of 1D OF system, but F internal is like F internal is a function of, it's a vector function of, or sorry, yeah, F internal is a function of U1, U2 up to UN. So what is the equivalent for F dash? Okay, that I can tell right away. So use the multivariable Taylor series, right? So how did we do initially? We said f of u plus delta u or un plus delta un is equal to f of un plus f dash of un times delta u plus and so on. Now equivalently, what is it for multivariables? F of u1, just take 2, maybe 3, right? U1 and put an n denoting the iteration number and add, say u1, u2, un are the solutions and the current iteration is slightly away from the solution. So you say plus delta u1 plus delta u2 plus delta u3. This is equal to what? It is f of u1, sorry, f of u1, u2, u3 plus what are the terms in the Taylor series? Multivariable Taylor series.
Oh, sir, unable to reconnect.
Okay, no problem. So this is just dou f dou u1 delta u1 plus dou f dou u2 delta u2 plus dou f dou u3 delta u3 plus dou square f by dou u1 square, delta u1 square by 2 factorial plus dou square f by dou u2 square delta u2 square by 2 factorial plus dou square f by dou u3 square delta u3 square by 2 factorial plus dou square f by dou u1 dou u2 delta u1 delta u2 plus dou square f by dou u2 dou u3 delta u2 delta u3 plus dou square f by dou u3 dou u1 delta u3 delta u1, and it will have the higher order terms. It will have the higher order terms. So again, as in this case, we will truncate it with the linear approximation. We'll truncate it here. So what is it? We'll get f is equal to, this is f internal of u1 plus delta u, u2 plus delta u2, u1, and u3 plus delta u3 is f of u1, u2, u3 plus, can you write it in some form? You can write this as
Matrix form.
yeah, you can write it as a product of a row matrix and a column matrix. You'll get something like this. So this is for a scalar f, but f also is a vector, right? You have a force vector. So f internal is also at every node you will have internal forces, net internal forces. So this is a vector, which means you'll have f1, f2, f3 internal. So it's like f1 of u1 plus delta u, delta u1, u2 plus delta u2, u3 plus delta u3 is equal to f1 of u1, u2, u3 plus dou f1 by dou u1, dou f1 by dou u2, dou f1 by dou u3, delta u1, delta u2, delta u3. Similarly, f2 you will have one expression, f3 you will have one expression. So finally you can say f vector, which is a function of u1 plus delta u1, u2 plus delta u2, u3 plus delta u3. This entire vector is f of u1, u2, u3. This is also a vector. So if this is n cross 1, this is also n cross 1. Plus what? Plus. So the first row will be, this matrix is common. Yeah. So this matrix will not change. It is delta u1, delta u2, delta u3. And the matrix will be dou f1 by dou u1, dou f1 by dou u2, dou f1 by dou u3. Then you will have dou f2 by dou u1, dou f2 by dou u3, and so on. You will have it for all four terms. So this is called the Jacobian matrix. So that is the reason I use J for the derivative. When you have just a 1 degree of freedom system, the Jacobian matrix will be 1 cross 1. So it's a scalar, J. And in other cases, you will have a matrix. It's a Jacobian matrix. So in the multi-degree of freedom system, what we'll have is you want to set this equal to 0. So the idea will be you want to set R of un plus 1 to go to 0. So you will say R of un plus in matrix vector form. Now R is what? R is this minus this, right? This minus this is the residual. R of un plus what will you get?
Jacobian times.
Yeah, this is the Jacobian. So this is not one. This is like n components of R, each partial derivative with respect to n components of u. So I can put it as Ri uj, something like that. Okay, so this is the Jacobian matrix times
un.
Yeah, delta uj, which is the increment. This should be equal to 0. So what is delta u? Delta u is
minus R of un divided by Jacobian.
No, you can't divide by a matrix. It is Jacobian inverse, right? J is a matrix, so you cannot divide by a matrix. It's just inverse. And what inverse? It is inverse on the left side. You can because matrix. This is a vector. You can't multiply it to the right side. So it is R of un. And again, un plus 1 is un plus delta u. So this is the idea. So get the force residual, find out the Jacobian, invert the Jacobian. Now this is a linear system. The solution for delta u is a linear system. For u, it is not a linear system. Now this Jacobian matrix for structural elements, it has got, okay, that will do too in the next class. It's too much. But the idea is the same. In the Newton-Raphson iterations, the entire truss program or the beam program will get into a loop. And in that loop, the truss program will mainly compute the internal force, depending on the current length, current angles, etc. But that is not the only thing that is required. You also need the Jacobian matrix. So it will also compute the Jacobian matrix, which is called the tangent stiffness. And once you get the tangent stiffness, you can get an update. Then this entire program will be repeated n number of times until this convergence criterion is met. So yeah, this code is also uploaded and I can stop here. So if you have any doubts, you can ask me. This part is a little technical. You have to really practice coding for this. Otherwise, this will be hard. And yeah, I said I will upload some homework type assignments, but I have not done it. I'll do it very soon. Maybe even after the last class, you can do and just submit on that. Maybe we'll not have sessions on that, but I can give you some feedback on whether the answers are correct, or if there's any issue, you can write on that classroom group. So yeah, so keep practicing, then it will be helpful.
Thank you, sir.
Yeah. Stop recording here. Thank you.
It is similar to Jacobian in mathematics.